Good afternoon, everyone. Welcome to the talk on gRPC proxyless service mesh, upcoming features for connecting to serverless services. I am Kannan Jayaprakasam. I work at the Google Bangalore office, and I work on the gRPC Java team. We'll do a bunch of introductory concepts on XTS and PSM. gRPC, as you're aware, is a high-performance RPC framework, and service mesh is a dedicated infrastructure layer that controls service-to-service communication in a distributed application. How many of you here are familiar with what service mesh is or already have used service mesh? Okay, that's a bunch of folks here. So we are basically going to build upon some of the concepts that exist in gRPC already for supporting service mesh. So a service mesh abstracts the application code from the network aspects of the communication, and it can be implemented either as sidecar proxies such as Envoy, or in the case of gRPC, this capability exists in the RPC framework itself. XTS is a control plane protocol to configure a mesh or a bunch of different nodes. It came out of Envoy, and it was how different control planes could configure Envoy as a sidecar. It's basically a watch-based API to get configuration updates from the control plane. Most of the interesting parts are more in the resources themselves than in the protocol itself. There are a couple of different implementations of control plane. There is the Google's traffic director, Istio, and there's a Go control plane. All these use XTS to push configuration to gRPC. So with gRPC, you're able to get the configuration from the control plane and use them for the aspects of communication. The X in XTS, basically, it's a variable. It stands for different resource types, and different load balancing policies apply at each level of discovery. Like we have listener discovery, route, cluster, and endpoint discovery. We'll just touch upon what each of these mean. LDS resource denotes a L7 load balancing configurations for a particular backend service application, whereas RDS is a route discovery. It denotes routing config for virtual host in a particular service, in a particular backend service. CDS is a cluster configuration of either logical DNS names in a route, or it's a cluster of EDS resources that themselves contain the endpoint addresses that you will connect to. And how these XTS resources get created on the control plane? Basically, there would be some certain configuration APIs, such as Google's own service routing APIs in the case of Google, or it could be it could differ based on whatever the service provider supports to configure the control plane with these resources. Now, service-to-service security. Service-to-service security. What does gRPC PSM security offer? So this is an existing offering for MTLS communication and our talk is going to build on top of these existing security features. So I'm going to touch a little bit on the security offering that exists today. For MTLS authentication or mutual TLS, both parties must acquire the other party to present their certificate. And both certificates to be presented and the trust store location to be used are pushed to the XTS clients by the control plane. So you don't have to have all the code for to know where to load these trust store locations from. Authorization can be configured by requiring the peer cert to belong to a particular workload domain called SPIFFE identifier. There's a previous KubeCon talk by Sanjay Pujare from Google, which you can refer to for the current existing offerings in gRPC for security. This is a high-level overview of the entry and flow of a MTLS communication. This picture shows the components that are involved in making a XTS-managed proxyless service mesh security offering work. So on the left, you have a yellow box, the client, which needs to send RPCs to the server on the right in red over a secure channel. The client and server needs the certificates and the keys that are provided by the certificate and deployment infrastructure to make this all happen. So there is a certificate and deployment infra that is shown in the green box below. And then on the top, you have the XDS control plane. So both these things together make all these MTLS communication configurations happen seamlessly. So there is a certification authorities, aka CAS, to mint the certificates, and there's a process to continuously generate CSRs and use them to mint the certificates before expiry, and a mechanism to make these certificates and keys available to gRPC using gRPC's file watcher plugin mechanism. When all these things are put together, the client and server are able to secure their gRPC traffic. This is MTLS. Now, for the purposes of this discussion, though, the main takeaway from this picture is that both client and server are XDS enabled, which means they talk to the control plane to get all the security configuration from the control plane. And we are going to basically talk about how this the new features that build up on top of this for talking to serverless. Now, as a continuation from the previous slide, we talked about this, the control plane's communication, pushing the security configuration to the XDS client, which is either a gRPC client or a server, about the security configuration to use for a particular connection. The trust store to validate the certificates presented by the other party. So it's basically there's an envoy proto which we are going to enhance. So this certificate validation context, which is part of CDS data, the cluster configuration data, that contains either of these two fields, trusted CA, or it's a name of a plugin, the certificate provider instance plugin name. That's what exists today. And in the upcoming slides, we are basically going to enhance this. Now, first of all, a little bit of coming to the problem, a little bit of background about what is serverless and why we want to connect to serverless. So serverless backends are services that are scaled on demand and sit behind a reverse proxy. Examples of serverless are Google Cloud Run and AWS Lambda services. Why does serverless services need a reverse proxy? Because we are going to see there are some of the problems are coming up, are existing because there is a reverse proxy. Serverless services being on-demand elastic services, there may be zero instance of a serverless service at any time, and they are spun up on demand. And hence, there's a need to receive incoming traffic via the reverse proxy, and then spin up instances of those serverless backends as needed. However, the problem space we're addressing in this talk is not unique to serverless. Other reasons can exist for using reverse proxies, such as for providing server-side load balancing or for enhanced security. Now, the first problem that talking to serverless backends presents is server certificate validation. Now, we want the gRPC service mesh expand its reach to serverless workloads in a secure way. So in this picture, there's a serverless backend named app1 and app2 on the right. And there's a reverse proxy shown in red that sits in front of these serverless backends. And now all the incoming traffic terminate at the reverse proxy, and which then internally talks to the serverless backend to which the traffic is directed at. There is no direct communication, no end-to-end connection directly from an external party to one of the serverless backends. So, and the client, which is shown on the left, is in yellow, is a mesh client, service mesh client, that is bootstrapped with the configuration for the control plane. So it can receive the configurations, security configurations from the control plane. And as shown in the previous slide, there is a below the client, there is a managed CA. This CA is managed, and it has a key store available through the gRPC file plugin mechanism. Now, so this being the existing setup. So what is the problem here is there is a proxy, the reverse proxy certificate has been issued by a public CA, which are commercial certificate issuing authorities like Verizon or some other. The problem is that the managed CA routes do not include or chain up to one of these public CAs, which means the client cannot establish the server certificate's validity. So the certificate chain cannot be established, and so the solution that we have developed is the mesh client needs to be instructed by the control plane in this case to use a different trust store, not the managed CA cert pool that we talked about before, but its own trust store, also called system root sets, which would have the CA roots for containing the certificates of these public CA authorities, not the managed CA certs, which is private to that particular network. The control plane can indicate in the cluster resource, return to the mesh client's CDS watcher to use system root certs instead of CA trust store or a provider plugin. So basically, the config plane APIs would have configured previously the CDS resources for the serverless backends on the control plane to make this possible. For example, when Google Cloud's service routing APIs are used to create routing resources on the mesh for a serverless, which is, in the case of Google Cloud, is the Cloud Run service, the configurations would have been created on the control plane called Traffic Director, which is Google's XDS control plane. So the proto I showed you before, so basically we are adding a third field, which will be used only in the absence of the first two. So this third field would basically indicate that system root certs have to be used. So this will cause the gRPC client to use for SSL handshake the trust store from its system root store and authenticate the server certificate chain. So here, so the change in this picture is that the CA cert roots shown on the left below the client is not the managed one, but it's a system root cert, and the control plane, that has been configured with the network resources for serverless, since the CDS config that contains the certificate context, the envoy proto, and that says to use system root certs. When the TLS handshake for the transport is established, gRPC client uses system trust store for this validation. And I'm handing off to Sreenithi now.
Hi everyone, so I am Sreenithi from the gRPC Python team at Google Bangalore. So I am going to continue on the second problem that we have in this case, which is having multiple backends behind the same reverse proxy. So the problem here is that we have a data plane RPC initiated with the endpoint IP address of the reverse proxy. But when we have multiple backends behind this reverse proxy, the proxy needs to know which traffic needs to go where, and that is what we're trying to solve. So what can you think of a solution? The way is that we could try to find a way to specify the exact endpoint host name along with the IP address. So that brings us to the next question. How do you find the IP addresses of the backend services in the first place? So that's what we'll look at next. So the endpoint host names are received during XDS name resolution at the control plane, like during the channel creation. So what this means is that as part of the service creation, service discovery, as Kannan explained before, we have different responses, different configs coming from the control plane, like the LDS, RDS, CDS, etc. So as part of this, we have certain configurations being changed here. So the RDS config first has a new flag called allow authority rewrite that needs to be set, because now we are setting an additional host name along with the endpoint IP address, right? So to know that this is what you're going to do, we have this extra allow authority rewrite flag. And after that, now coming to the actual endpoint host name resolution, There are two ways that can be done based on what the destination is, like if it's a logical DNS cluster or an EDS resolution. If it's a logical DNS cluster, we have we have that RDS config, and then in the CDS config, there is the logical DNS endpoint hostname coming in there. So we don't have an EDS resolution, but only a logical DNS resolution for the endpoint hostname. But in case of but in the case of the EDS resolution, what happens is the CDS config will have the EDS resource name itself. So here we directly have the endpoint coming in from the EDS response. So this is how we have the EDS, the endpoint host names. Now coming back to our first question. Now that we have the host names, where do we set it? We set it at the control plane level. We set it at the data plane level when we are doing the actual RPC call. So, So now from the diagram, you can see that we have the control plane, we have the RDS flag, the endpoint hostname, everything coming in. And every time we have an RPC going out, the load balancer will put in these flags at the authority header. So that's what we kind of see here. And once we do that, it pretty much solves our problem that we were talking about. We have the request going to the reverse proxy. The reverse proxy can use the endpoint hostname to further, further route it to the right backend. So yeah, and now giving it back to Kannan for the next problem.
The third problem is client authentication by the serverless backend. The serverless backend service needs to authenticate and authorize its calling mesh client. Normally in a MTLS solution, what we would have authentication through client-side certificate validation. The server requires the client to present the certificate, and it would validate the client. And authorization is done via workload SPIFFE identifier. So the server can use an authorization policy that requires the caller certificate to belong to a particular allowed domain, called a trusted domain. Now, in the case of calling a serverless service, client trailers cannot be used because the mesh client uses private managed CA issued mesh certificate, which cannot be understood or validated by a serverless backend. So for authentication, we need to rely on jar tokens. This authentication mechanism is either one that is supported by the serverless infra, or when it is not available, then on the gRPC server itself, one could add a server interceptor for the jar token for validating it by calling the identity provider. gRPC, now for the implementation of how this is done from the client side, the gRPC already supports specifying XTS HTTP filters for the HTTP connection management in the LDS config. And in the same framework of HTTP filters, gRPC will support authentication filter to use for the L7 layer security. gRPC client will have a plugin-based registry of available authentication credential implementations with identifier for each, and the auth filter config that is received by the control plane will specify this identifier, which will cause the corresponding implementation to get used, and that will use a specific identity provider to create the jar token. And this jar token can then be attached to the outgoing RPC. The jar token is not an opaque token. It will encode a particular piece of information from the CDS data called an audience. It's an identifier. This identifier can be the URL of the service itself, or some identifier that the service can identify itself as. LDS config, basically, so in this picture on the left, the top box is the LDS config that indicates the auth filter config through a type URL, and gRPC maintains a list of a registry of filter types and their call credential implementations, and the cluster metadata that is received through CDS will have the audience string that needs to be used, and so this is the control plane stuff, and the per RPC, there is a filter that runs per RPC. This one? Oh, okay. Yeah. So this is the data plane that is per RPC. So the per RPC will run the call credential code belonging to that particular filter type. So that calls the YADC identity server using the service account credentials, and it will also pass along the audience to encode into the jar token and receives a jar token from the identity service. And it's attached to the outgoing header, the authorization header. And on the target side, the service receives verifies the jar token signature using the cloud provider's infrastructure. In addition, it also extracts the audience and verifies that the audience is denoting itself. So this is to avoid replay attacks. And then for authorization, there is an additional check that is done whether the calling service, the service account is authorized to call this serverless backend. So that completes authorization. Now gRPC will have an inbuilt authentication provider or the call credential implementation for GCP services that use Google as the identity provider. For other cloud providers, external contributions can be made using the same framework. Now, in summary, we have solved authentication through signature verification of the jar tokens, and for authorization through service account permissions to call the backend service. Now, for the roadmap of these features that we talked about, the gRPC features for serverless are coming up in a public preview end of Jan 2025 in C++, Python, and Java. And for Go, it will be available in GA at a later date. I'm handing off to Sreenithi for the demo.
Thank you, Kannan. So I'm going to continue with a quick demo of whatever we have discussed so far. So while we don't have a very live demo here, I'll just go through all the different code concepts and different elements we have to get everything working. So the first we have is, of course, the server. And as we first discussed, on the server side, you don't need any control plane managed security config. And so on the server side, we will be creating, we don't need to mention anything about XDS credentials. It will just be insecure server credentials being used. And on the client side, auth and auth are handled by a component called Cloud Run Sidecar. So the service implementations don't have to worry about them. And now that we have the server, let's start about deploying stuff. So now the next step is about deploying the service in Cloud Run and creating a service mesh. We have the gcloud commands there. And next is we will have the network resources being created. That is nothing but we first create the network endpoint group, the backend service. The first command is the network endpoint group. Second is the backend service. And the third is deploying or adding that backend to the network endpoint group. So that's like step 2. And now the final part would be about configuring the routes itself using the service routing APIs. So we have the route set up here, and these resources would be used by the control plane for configuring the XDS client watches. So that was all server side, and now let's get to the client side. Before we get to the client code, let's look at the client bootstrap configuration. I know this is probably not zoomed in, but okay. Before that, let me also give a brief of what a bootstrap file is. For those who don't know, it's basically a file that will be generated on the client side, and the client can refer to that file for the server URI that it has to create channels to. So in this case, let's zoom in a bit, and the XDS servers, that part of the file will specify the URL of the control plane, which in this case is of the traffic director. So now finally coming to the client code. So unlike the server side, on the client side, we do need to specify the XDS credentials so that we get the required security configuration from the control plane. So that's what we define here. And finally, now that everything is set, let's look at the success response case. So we have the first line, which is about using the bootstrap file, and then all the 3 different problems and solutions that we were talking about so far. We enable all the solutions using environment variables right now, the authority rewrite, the system root certs, and the authentication filter. And doing all that, what we see here is the direct response from the client, but let's also go a little deeper and look at the different configs that we get from the control plane. So, so the first thing that we have is the LDS config that we have from the control plane, and as we specified, the LDS config has the auth filter enabled. So that is from the LDS config. Second thing is the RDS. Remember, I had spoken about that extra authority rewrite flag. So that's what we have here. Finally, we have the CDS config. And again, I spoke about the logical DNS and EDS responses. In this case, we have the logical DNS config, and that's what we specify in the host name. That's the first line there. And the second one is the system root certs that you can see that's coming in from, we have that enabled. And finally, we have the audience that specifies the GCP auth filter. So we can see how using all this, we're able to successfully communicate between a serverless backend and a client. So that's it. And thank you, everyone, and hope we see you again for all the next talks. We have a maintainer talk coming up right after this in room 404, and also one other talk on OpenTelemetry for OpenTelemetry tracing tomorrow. So hope to see you all there. Thank you. And finally, any questions?
From the demo, I realized that it's using Cloud Run, right? But are there any plans to make it cloud agnostic? Let's say a lot of people are using Lambda and service from Azure, right? And like looking into the architecture seems like a sidecar is required from the cloud provider's point of view, right?
The solution we presented is already cloud agnostic. The demo is just showing a particular implementation at Google that is Cloud Run. But all the control plane communications that we talked about, as long as it's implemented by the control plane of a different cloud provider like Amazon, like AWS, as long as it talks XDS, the same solution applies. The only implementation that gRPC natively will not have is the GCP authentication filter. Someone will have to implement it, but the solution is generic already.
Projects to do this with Knative or something like that? Sorry. So as you mentioned, as long as the cloud provider has that sidecar that you mentioned and this is supported, it will work. But what about something like Knative? Like, is it possible to like emulate this behavior with serverless on Knative or something like that? Like on local cluster, for example, just to simulate or just to understand how it works. Is it possible to do it on a local cluster is there sidecar available as an open source project or something similar?
Hey, Richard, maintainer on the gRPC project. One thing that I want to make clear is everything here was done, a little bit flaky, was done without sidecar on the gRPC library. So while there may be a component within Cloud Run that sort of incidentally acts as a sidecar, that is not essential to what's happening here in sort of just traversing the reverse proxy.
Any more questions? Awesome. So again, thanks everybody. And I do want to invite you up to room 404. We'll have the gRPC maintainer talk. And what we're going to be doing up there is we're going to start with an overview or kind of an intro to gRPC. And then after that, we're going to transition to telling you about all the new exciting features we have for gRPC. So thanks everyone.